Oh. Oh.
Yeah. Let's see here. Welcome to class. It's rainy weather.
Oh, I hate it.
It used to be like this all the time. Like every winter was just like rain, rain, rain. It hasn't been like that as much the last few years, but this used to be a very typical day of this weather. It's not that bad.
Well, seeing as I come from a place where it never rains.
It's rained
I
there
used to love
occasionally.
rain, and then I came here.
Sure. We can start in a minute here. Oops.
Good nuts.
This thing is so chalky. Okay. I'm moderately surprised that there's no one online, which is totally fine, but just weird. Considering there's a number of students who signed up for the class, but I get it. It's the first day, and you know it's gross outside. Anyway, are we recording? Yes, we're recording. Cool. So everyone's in the same 16C class, right? There's one class. Who's teaching it? It's Varn. He's good. I mean, I don't know him personally, but I've definitely taught co-classes for classes of his before, and he seems to do a good job, and the students seem to like him pretty well. So should we get his class met already or not yet?
Yeah.
Yeah.
Just before this.
How was it?
He's one of the syllabus.
Sure. Yeah. Okay. Let's see.
Also hard to tell where his where his sarcasm starts and where his actual voice begins.
Okay, that's fair. Yeah. I've heard he's funny, but like again, I've never really seen side action. This thing is really like, is it this? No, it's not. I wonder what's causing all this shaking. Yeah. Huh. Interesting. I mean, yeah, that makes sense. I wonder. I'll have to have someone look at that because I mean it's not terrible, but it's kind of funky. Let's see what else. So I mean, for those of you watching the video later, because there's hardly anybody here, I'll just remind everybody to please fill out the attendance form whenever you come to class. I did away with my own QR codes, so you can actually just use the one that's right there. Please do so. It's also linked in Canvas. I do encourage you just to bookmark the link. So don't use if you took 16B last quarter with me, don't use the link from last quarter, even though it's still live. Use the link that's in every AATC classroom and that is also given to you in Canvas. If you want to look here, you can see, if you look at the 16C workshop Canvas page, if you go over to the modules, which is what will be the homepage eventually, and you can't see this yet, but there's some useful links. The first one is the link to class. The next one is to the attendance form. So if you're filling out the attendance form, that is an easy way to get there. But I would really just say bookmark it and just do it every time. I'm not going to keep track of your attendance. You won't see it in Canvas because this class doesn't have any sort of grade at all. It's just you're coming to get help whenever. So that said, please still do it. I'm more talking to the video because I know you two have done it already. But like if you're watching this video later, also even when you watch videos, please do fill out the attendance form. So yeah, let's see. What else?
I think I know the issue.
Oh yeah?
Yeah.
What's up?
Well, there's something in the way. I thought there was like
That's a good guess.
string that was like the air was going on it.
Yeah.
I don't know.
And these things definitely can be sensitive. Apparently, like if you jostle them too much, they will like there's no alarm will go off. It's like they want you to steal their expensive projector. Yeah, right. It says right there, alarmed. Yeah.
through Bretton Hall with a BB projector.
Right. Well, I guess, I mean, we might as well just jump right in, right? So I haven't gotten onto your professor's Canvas yet because he's probably busy and hasn't gotten there yet, which is totally fine. But I imagine you guys will probably be sticking, oh wait, that's not how, there it is. So let's take a look. Let's see what your Math 16C also looking like. Let's see. I usually go look at assignments if there is such a place to look. I don't see it yet. That doesn't mean it won't be there eventually. Or modules. No, you know what? That's definitely your class's Canvas. I don't see anything that's super useful at the moment though. Do you all see anything? Announcements. Hi all. Yeah. Sure, yeah. I imagine you all still haven't gotten your grades for 16B.
No.
Yeah, I don't think anyone has, which is rough, but I'd like to imagine your instructor last quarter is doing their best to get it done as soon as they can, but I'm sure it's not a small task to accomplish. So yeah, but yeah, so it doesn't look like the Canvas for your class really has anything useful yet. I'm imagining some people would wait till the last minute to set their Canvas, which is totally fine. But yeah, your professor probably
One of my Canvases isn't even published yet.
right. Well, I imagine a lot of your professors last quarter are probably still trying to get the work from last quarter done. And so getting the stuff, I mean, right, winter quarter, everyone's like, we know what's going on. You can wait on the Canvas. So yeah, let's jump into the math. Also, I guess, well, I mean, you can find me in various places. My office hours are listed on Canvas. I have office hours right after class today in C class, which is over in the MU. But yeah, if you can find where to find me, well, that's kind of blurry on yeah, interesting. Why is that so blurry? Okay, it's not anymore. You can find me in the usual places at times, but if you're curious about where to find me, you can just look at Canvas. My office hours are listed at least a couple times on there. You can also look at my website, which is not very good or very informative. It's informative. It has where I am and when I'm there, but like it's not great. Anyways, do you guys have any questions? How was your winter break? Good. Definitely. So I will let you all know. Is this your first year at UC Davis? Yeah. This winter break was an exceptionally long winter break. Don't get used to it. The year before, the winter break was more like exactly 2 weeks. So that's more typical to be like 2.5, maybe 3 if you're lucky. So this winter break was definitely kind of exceptionally long because of how the calendar worked out. So just be prepared next year for winter break to maybe be not quite as nicely long, which is too bad, but it's what you get. So yeah. Okay. Let's talk about the pen on my hand. Where'd that come from? All right, anyway. Let's talk about differential equations. So I'll try to write as nicely as I can. So here is an example of a differential equation. Y prime plus 5y is equal to 0. It's a pretty straightforward one. It has a lot of possible solutions. There are a lot of different functions, y equal to some function of x or t or whatever variable you like, but typically x is the variable you use, that could be a solution here. I also want to point out that e to the x is going to come up a lot because e to the x is its own derivative. And so that kind of answer is going to be very prevalent here. So I just want to point out that e to the x comes up a lot because we know that the derivative of e to the x is equal to e to the x. So I'm going to tell you a solution. It's not the only solution, but it is a solution. So here's one solution. This table is a little low. One solution is y equal to e to the negative 5x. So let's check to actually see the solution, because a lot of what this beginning section is about is just verifying that a function is a solution to a differential equation. So to see that this is a solution to that equation, not only do we need the function y equal e to the negative 5x, we also need the derivative because we're going to just substitute those back into the equation and see if we actually get it equal to 0. So let's also find y prime. So the derivative of e to the negative 5x is e to the negative 5x times the derivative of negative 5x, which is negative 5. Or as most people would probably write, y prime is going to be negative 5 times e to the negative 5x. Okay, so let's try subbing those back in to this original equation and seeing what we get. So let's see here. I've got y prime, which is negative 5 e to the negative 5x plus 5 times y, which is 5 times e to the negative 5x. And if I add those together, I do get 0. They totally cancel each other out. So that is one of many solutions to this differential equation, but it's definitely not the only solution. So another solution could be, let's try, what do I got here? Yeah, let's try that. Let's try y equal to 3e to the negative 5x. Well, in fact, why don't you try it? Take the derivative, see what you get, plug it into your differential equation, see if it's equal to 0. To check out. No, I know I should know your name. I totally don't know your name.
My name?
Yeah,
Caroline.
Caroline. You have an older brother that goes here, right?
Mhm.
Yeah. He's mentioned that he's like, I think my sister's in your class.
Oh,
Yeah,
yeah.
pretty sure she is. Caroline. Okay. So this works as well, right? If we take the derivative, y prime is going to be, well, let's see, the derivative 3e to the negative 5x is going to be negative 5 times 3e to the negative 5x. So we're going to get negative 15 e to the negative 5x. And if we throw those back into this differential equation, we're going to get y prime, which is negative 15 e to the negative 5x plus 5 times y, which is 3 times e to the negative 5x. And yeah, negative 15 e to the negative 5x plus 15 e to the negative 5x does indeed equal 0. So what this kind of leads us to see is that we can talk about a general solution to this differential equation. So any solution or a general solution is going to look like some constant times e to the negative 5x. Which also points out that there are, in fact, an infinite number of solutions to this differential equation, right? C could be any constant, positive, negative, rational, irrational, whatever you like. It could even be 0, which is kind of weird, but I will just point out that the function f of x equal to 0 is also a solution to this differential equation. Because if you take the function 0 and then take the derivative of 0, which is also 0, and add 0 plus 0, you do get 0. It's not a very interesting solution, but often it is a solution to your differential equation. All right, let's look at some more examples. So a lot of this beginning stuff is just showing that a function is a solution to a differential equation. For example, we can show that f of x equal to 4e to the x is a solution to f double prime of x minus f of x equal to 0. It's not always the case, but it is often the case that these differential equations are written as some manipulation of your functions and your variables equal to 0. Doesn't have to be right. We could have just as easily written this as f double prime of x equal to f of x, but often it is very kind of standard to just say everything equal to 0. Well, all right, let's do it. So I need to find, I've got f of x is 4e to the x. It's not very exciting. F prime of x is also 4e to the x. F double prime of x is also 4e to the x. So when I put these into this equation here, I'm going to get, I'm getting 4e to the x minus 4e to the x. And oh yeah, that definitely checks out to be equal to 0. So not particularly exciting, but worthwhile. We can also show that f of x equal to a constant times e to the negative x is a solution. It sounds really terrible out there. Did you? There's like a big, just like. Did you guys see the big tree that was like falling down behind the building?
No.
When you leave, if you have a moment, I encourage you going out the back doors and like that wall that everyone like takes their graduation pictures on. No, wow. So okay, so behind Dutton Hall, like behind the redwoods over there, there's like this little like wall that says like UC Davis, established 1955 or whatever, whenever it was established. I don't remember when it was. 19 whatever, 19, but that was back when it was like an extension of Berkeley. Yeah, so it might have a different year. Anyway, there's this little wall there, and like everybody and their mom takes graduation pictures there. Like there's like a line of people at the end of the quarter just like waiting to like go stand in front of the wall, take the picture, or whatever. So anyway, back over there, there's a giant tree that's like fallen over. So interesting to look at if you want to look at the fallen tree. Anyway, back to this. So we can show that this is a solution to the same equation. If we take the first derivative, well, now it's a little more effort because our function is actually a little different. It's c times e to the negative x. So the first derivative is negative c times e to the negative x. And then the second derivative is negative, negative. So positive c times e to the negative x. And then if we throw that in there to this differential equation, our f double prime of x minus f of x is going to be given by, let's see, f double prime is c e to the negative x. F of x is also c e to the negative x. And that's definitely going to equal 0. So a lot of times showing something as a solution to a differential equation is not very exciting. It just means you have to kind of take some derivatives and substitute them into your original differential equation. Let's look at a couple more examples. So no, it's not that important. That's a little important. So a more general solution, just because I think it's kind of interesting, you can show this on your own later, would be the following. F of x equal to c1 e to the x plus c2 e to the negative x, where c1 and c2 are different constants. If you take the second derivative of that and add it to the original thing, or sorry, if you take the second derivative of that and subtract the original thing, they will totally end up canceling each other out and you get 0. Really, like, I hope, I'm mildly curious. I'm not really that worried, but the fact that nobody is on Zoom makes me wonder if like there's a weird link problem, but I did open it from the Zoom link in Canvas, so you don't feel like there should be a problem. Okay, I'm not going to worry too much about it. All right, let's look at another example. Let's show that, in fact, why don't you guys do this one? Show that y equal to 3 cosine of x is a solution to the differential equation y double prime plus y is equal to 0. Bugs? No, that's loud. Okay, sure. Check that out. You can finish it. Okay, so let me ask you, what's the derivative of cosine? Okay, so good reminder, just so everyone knows, if your function, let's say if your function is cosine of x, its derivative is negative sine of x. And the derivative of negative sine is negative cosine, and the derivative of negative cosine is positive sine. And then the derivative of positive sine gets you back to cosine of x. Sine and cosine are always each other's derivatives. It's just you have to remember which one is negative, which one's positive. The way I always remember it is that, and this is true for all co-functions, cosine, cosecant, and cotangent, all of the three co-functions have negative derivatives. So just as it's a good time to remind ourselves, the derivative of cosine of x is negative sine of x. The derivative of cotangent of x is negative cosecant squared of x. And the derivative of cosecant of x is negative cosecant of x times cotangent of x. Whereas the, might as well fill in the list here, why not? Whereas the other three, the derivative of sine of x is cosine of x. The derivative of tangent of x is secant squared of x. And the derivative of secant of x is secant x tangent x. So all of the primary or the not co-functions, sine, tangent, secant, have positive derivatives, and all of the co-functions, cosine, cotangent, and cosecant, have negative derivatives. Good to remember. So then here, if we find y prime, the derivative of 3 cosine x is going to be 3 times negative sine of x, or more normally written as negative 3 times sine of x. And then the derivative of that is going to be negative 3 times cosine of x. So then if we add these two things together, oh, we have a person on Zoom. Yay, Zoom person. Welcome to Zoom. Welcome. Sorry. Put my video. Cool. So we're just verifying some differential equations here. So if we add y double prime plus y, we're going to get negative 3 cosine of x plus 3 cosine of x, and that is going to equal 0. Something else I was going to say. Nope, I guess not. All right. Oh, I know what it was. We'll get there in a second. So let's also, while we're at it, oh, there's something in the chat here. Hello. Yes. Yes, you're welcome to use the chat. You're welcome to unmute yourself and ask a question if you have a question. And I just want to make sure, can you see what I'm writing over here? Can you see my face? Cool. Good. Just want to make sure. I mean, I figured yes, but just want to make sure. So let's, for this differential equation, y double prime plus y equal to 0, let's go ahead and also verify, and I'm kind of running out of room here, verify that y equal to c1 times sine of x plus c2 times cosine of x is a solution. Or I suppose I could give you something crazy and be like, check to see whether or not it is a solution, right? Most of the time, this will be phrased as verify this thing as a solution, but someone could change it up a little bit and say, here's a function, is it a solution to this differential equation? And then you still do the same kind of thing, but it might not work out. So let's see here. If I take y prime, the derivative of a constant times sine is just that constant times cosine. And the derivative of a constant times cosine is negative that constant times sine of x, because the derivative of cosine is negative sine. And then if we take the next derivative, y double prime is going to equal, let's see, the derivative of cosine is negative sine, so I get negative c1 times sine of x. And the derivative of sine is positive cosine, so we get minus c2 times cosine of x. And then if I add y double prime to y double prime plus y is going to equal, let's see, negative c1 sine of x minus c2 cosine of x plus c1 sine of x plus c2 cosine of x. And those all cancel each other out. So this does equal 0, which means it is a solution to this original differential equation. Right. So sometimes we like to add a little bit of extra flavor to these questions by, well, like in the following example. We're going to say, let's do the following. First, we're going to verify, just like we have been, that y equal to c e to the 6x is the general solution to y prime minus 6y equal to 0. If I go ahead and do that. So as I mentioned before, the derivative of e to the x comes up a lot, or e to this something more complicated than just x, right? E to the stuff. And the derivative of e to the 6x is, of course, e to the 6x times the derivative of 6x, which is just e to the 6x times 6. So here we're going to get 6c e to the 6x. And then if we subtract those together, y prime is 6c e to the 6x. 6 times y is 6 c e to the 6x, and as is typical, they do the thing we expect them to do. And then a lot of the times after you have either verified or later on when we actually start finding solutions to differential equations, you're then going to find, so this is the general solution, c can be anything, but then we're also going to add an initial condition. So the second thing we're going to do is find the constant c so that we solve the particular solution for the initial condition. And I'm going to write it this way: y equals 4 when x equals 0. So typically what they're going to do is they're going to give you some, it's usually called an initial condition because it often refers to what the value of y is at the beginning. But really they could have given you any x equal to 1 or 10. Basically, as long as they give you some data point, it's called an initial condition problem because they're telling you we know the value of y at some place for x. Someone might choose to instead write this as y of 0 equal to 4. The same information, just written in a slightly different way. So when you read it this way or this way, it means the same thing, that we know that x is 0 and y is 4. And when you're given this, your job is to solve for the constant c. So let's see. So my solution, my general solution was y equals c e to the 6x. And now to find the particular solution, I'm just going to plug in those values for x and y and solve for c. Here it's really straightforward. Y is 4 and x is 0. So 6 times 0 is 0, e to the 0 is 1. So that ends up giving me c is equal to 4. Here's where you have to not stop. So they ask you for the particular solution. The particular solution isn't c equal to 4. The particular solution, just like the general solution, is still a function. So whenever you're talking about differential equations, it's really, really important to remember that the solution to the question is the function, y equal to whatever, or f of x equal to whatever. So my particular solution is y equal to 4e to the 6x. Just your general solution with the value for the constant plugged in. So whenever we're talking about solutions to differential equations, the answers are functions. you're looking for a function like y equals e to the 6x or y equals 4 e to the 6x or y equals sine of x, right? Those are the kinds of things that are going to be the answers to differential equations. Questions so far? I mean, it's pretty straightforward so far, but like if you have questions, definitely ask them. Let's see. Let's do another one. Yeah, I got a couple more. So sometimes I would say there's kind of two varieties of verifying something's a solution to a differential equation. Most of the time, or a lot of the time, they're going to give you like, here is your differential equation, and here is your supposed solution, y equal to a thing. But it doesn't always look like that. So here's another example. We're going to show that the general solution to this equation, x squared plus 2y cubed y prime equal to 0, is 2x cubed plus 3y to the 4th equal to a constant. Now, this seems kind of weird because what we've been used to doing so far is just taking whatever y is equal to, taking its derivative however many times we need to, and then plugging things back in appropriately. Technically, you could, it'd be dicey, but you probably, maybe, you shouldn't. One way you could do this, though, would be to solve this equation for y and then take the derivative and then plug it back in here. It's not what we're going to do, though. If it's written like this, it's a clue. And the clue is, when it's written like this, they're kind of tell you should use implicit differentiation. So let's take a look and see. So if we take our general solution, we're just going to differentiate 2x cubed plus 3y to the 4th equal to c implicitly. Because we're always making the implicit assumption when we deal with these kind of problems that your function y, or whatever we've called it, is a function of your independent variable x. Or maybe it's f as a function of t or whatever. But you always get to make that assumption, right? That the thing that's supposed to be the function is a function of the thing that's supposed to be the variable. So here, let's differentiate both sides. The derivative of 2x cubed is 6x squared. The derivative of 3y to the 4th, well, the derivative of 3y to the 4th, remembering that y is a function of x, the derivative of 3 times some stuff to the 4th is going to be 12 times my stuff cubed times the derivative of my stuff. Just like we used to do with implicit back in 16a, 16b. Was that? I don't remember if it was A or B, but whichever, I believe 16b. Really? B? Yeah. And then what's the derivative of c? Right. So now the only other thing you have to do is try to see, well, does this look like that? And there's kind of a couple of ways you can go from here. Depending on how different this looks, it might make sense to take this equation and solve for y prime. I don't think it does in this case, but it might in other cases. Here, you can probably see that this looks a lot like that. What do we need to do to this equation to make it look exactly like this equation? Right, divide everything by 6. If we divide by 6, we're going to get x squared plus 2y cubed y prime equal to 0. And that is exactly the differential equation. So this is a solution because when we take the derivative of both sides, we get the equation that is a solution to. It might feel like it might feel more like you were doing the actual work if you then took this equation here. So you could go this other way as well. Instead, you could take 6x squared plus 12y cubed times y prime equal to 0. And you could solve for y prime. You could say, okay, 12y cubed times y prime equals negative 6x squared. And then y prime equals negative 6x squared over 12y cubed. And you could reduce that down if you wanted to and say y prime equals negative x squared over 2y cubed. And then you could plug that into your differential equation and say, okay, does that make this work? Well, we're going to get x squared plus 2y cubed times negative x squared over 2y cubed. And oh yeah, those cancel. And you get x squared minus x squared, which equals 0, which is what it's supposed to equal to. So this might feel like you're doing more of the work to like show it, but you really don't have to do that. You can just take the derivative of both sides and make it look like the equation is supposed to look like. It's also kind of, it feels a little bit funky when you do it that way, but it's really totally valid. Let's see what else I want to say here. Oh yeah. And then we could additionally ask ourselves, okay, what's the particular solution? When, what do we got here? When y equals 1 and x equals 2. So when someone says particular solution, what does that mean we have to find? The constant. So whenever you see the words particular solution, you should think, oh, the problem means I'm going to have to find the constant. It might not always 100% of the time actually mean that, but it almost always does. So we want to find the constant, C. So, all right, so I'm just going to plug in 1 for y and 2 for x and get, like, it's really straightforward here. There's kind of almost nothing to do. I'm going to get 2 times 2 cubed plus 3 times 1 to the 4th equal to my constant. Let's see, that's 2 times 8 is 16 plus 3 is 19. Now, here's where things get a little weird. We then have to go back and plug that into our equation. So here our particular solution is kind of funky because we don't have y solved for. But our particular solution is 2x cubed plus 3y to the 4th equals 19. Sometimes when you find a particular solution to a differential equation, you won't be able to solve for y. Here you could, right? You could totally subtract 2x cubed, divide by 3, and take the 4th root, although there's a plus or minus issue there with that. But generally, if you have something like this where you can't solve for y, it's okay. You say, well, this is the solution to my differential equation. It's kind of weird. Let's look at this next example. Yeah. And then yeah, we might as well. We got time. Yeah, sure. We got time. I got one more that I came up with myself. It's kind of funky. So let's show that y equal to x squared times sine of x is a solution to the differential equation 2y minus xy prime plus x cubed cosine of x equal to 0. I'll remind you, so when you find y prime, I want you guys to try this one on your own. To find y prime, you're going to need to use what? What derivative rule? Yeah, product rule. So go ahead and find y prime. And then after you find y prime, plug in y here, plug in y prime there, and see that you get 0. I should have written this as check to see if this is a solution because I made it up and it could be wrong. I don't think it's wrong.
It's not.
Oh, good. But you know, when you make up your own problems, you always worry that maybe you made a small mistake. Let's check here. So the derivative of x squared times sine of x is 2x times sine of x plus x squared times cosine of x, just using the product rule. And then if we substitute in y, so by plugging in y, I'm going to get 2 times x squared times sine of x minus x times y prime is all this 2x sine of x plus x squared cosine of x. And then I still have my x cubed times cosine of x. And I don't like to actually say it's equal to 0 until I'm sure it's equal to 0. So I'm just going to simplify. I've got 2x squared sine of x minus 2x squared sine of x minus x cubed cosine of x plus x cubed cosine of x. And then I can see, oh yeah, that's going to cancel with that. That's going to cancel with that. So that does equal 0, as it should. Cool. So showing something is or is not a solution to a differential equation is usually not too terrible. It really just consists of finding whatever derivatives you need to and substituting them into the problem. Or potentially, if it's something like the previous problem, taking your funky equation and just differentiating the whole thing straight away. Like if it looks like something you can't just solve for y easily for, they probably want you to just use implicit differentiation. So keep that in mind. It doesn't come up a whole lot, but it comes up every once in a while. That said, you're not always going to be given the solution to a differential equation. The more important part of the process typically is actually learning how to find solutions in differential equations. So let's look at some examples. And I've got some interesting some paper here that's paper with things on it. Scratch paper. Okay, that's fine. One way doesn't always work, but one method of solving a differential equation and again, the differential equation, I guess I maybe should have said what a differential equation is, but in case you haven't noticed, a differential equation is just an equation that involves a function, typically we call it y, and one or more of its derivatives, y prime, y double prime, et cetera, et cetera, et cetera. So that's what a differential equation is. It's an equation where we're trying to find the function y and it has its derivative in there as well, or its second derivative, or both. Most of the time in this class, we're going to be limited to just having the first, like ones where we're actually solving them, it'll only have the first derivative of your function in there. You won't have anything more complicated than that. But there are whole entire fields of study dedicated to solving differential equations. We have a very limited scope in this class. We're just going to look at 2 types really. But one of the types is by what's called separation of variables. Or we might say the differential equation is separable. And people often abbreviate differential equation by diff EQ. So let's look at an example. Here is an example of a separable differential equation. Y prime is equal to x plus 1 divided by y squared. And typically, if you're thinking you might want to try separating variables, it's almost always to your benefit to rewrite the differential equation as dy dx instead of y prime. Because the idea is literally that you want to separate the x variables from the y variables. You want all your x's on one side, all your y's on the other side. And I will specifically mention that the dy's and the dx's need to both be in the numerator or in the top, meaning we don't want this dx in the bottom. So whenever I write a differential equation like this, and I think it might be separable, I'm always going to write dy dx on the left. You don't have to, but if I do it always on the left, I know that I want my y's to always end up on the left side and my x's to always end up on the right side. And the first thing I typically want to do is get rid of the dx on the left. So I'm going to multiply both sides by dx. which I know is kind of a hand wavy-ish thing, right? It's not really a fraction. It's kind of funny. This dy dx thing, this derivative, we always talk about how it's not a fraction, but we almost always treat it like it just works like a fraction all the time because it does. So even though it's not a fraction, just treat it like a fraction. It's going to do all the fractional things you want it to do. So we're going to multiply both sides by dx and get dy equal to x plus 1 divided by y squared times dx. Now I haven't fully separated my variables yet because I still have some y's on the right. So how am I going to get those y's over to the left? Well, I'm going to say this a few times. The only things you're really allowed to do when you separate variables are either to multiply or divide. Adding, subtracting don't really work because, well, you'll see in a minute why. I'm going to multiply both sides by y squared. I'm going to get y squared times dy equal to x plus 1 times dx. And the reason you can't add or subtract is because once you get to this stage, you want everything times a dy or times a dx so that you can then integrate both sides. So this leads to taking the antiderivative of y squared with respect to y equal to the antiderivative of x plus 1 with respect to x. But if you had like dy plus y squared, you can't really do the anti-differentiation there because you need the dy to be connected to the thing you're anti-differentiating. So just remember, when you're doing separation of variables, you can only multiply and divide. All right, and then we do the thing. We anti-differentiate, we get the antiderivative of y squared is y cubed over 3 plus a constant. And the antiderivative of x plus 1 is x squared over 2 plus x. Plus, let's call this one C1 and this one C2, a different constant. Now here's what really happens. Typically, we're trying to solve for y if we can. And so although you can write C1 here and C2 here, the next step would be then to subtract C1 from both sides. And then say this constant over here, C2 minus C1, is just a new constant. Let's call it C. So what we really typically do in practice is when you integrate the y side, don't write a constant on that side. Just say you've got y cubed over 3 equal to x squared over 2 plus x plus a constant. And then we do our best to try and solve for y. So I'm going to multiply both sides by 3. So y cubed equals 3x squared over 2 plus 3x plus, you could write 3c, but since 3 times a constant is still a constant, most times you're going to see professors just write c again. If you really like, we can call this one here, like this one can be c3 and this one can be c4 to kind of like indicate how they're changing each time, but we're still just calling them a constant. We don't let that throw you off, right? When someone multiplies a constant by 3, we just call it the same constant usually, even though it's slightly different. And then finally, to solve for y, we're going to take the cube root of both sides. Now, the nice thing about a cube root is you don't have to worry about like a plus or minus, right? If it was y squared equal to some stuff, we'd have to write y equal to plus or minus the square root of something, and then the initial condition would probably make a difference here. But here we're just going to get y equal to the cube root of 3x squared over 2 plus 3x plus, I'm just going to say a constant because we've gotten to like the last step. I don't need to like keep track anymore. So there's my general solution to this differential equation. We're not going to check it, but you could. If you really wanted to, you could take the derivative of this, which would be kind of gross, plug it in there, and then see that it's equal to x plus 1 divided by this thing squared. It's not too terrible. It's a little terrible, but it's totally reasonable to do. But not in the negative minutes we have because time's up. So last thing I'll say is you can find the initial condition if we're given that y equals -2 when x equals 0. You should all be able to figure out that c is going to equal -8. I'll let you do that on your own. If I start going over time, let me know. I gotta remember it's 10:50. So that is all we got for today. There's a possibility that we won't have class on Friday because I might be going to see my brother on Friday. I will let you know. I think we're not going to go this Friday because the weather seems terrible, but I will certainly let you know if there's not going to be class Friday. But if I don't say anything, just assume there will be.